Okay, so now in the last part of the code, I want to do a couple of simulation studies that sort of it's a preview for what's coming in the course. It's to compute a sample distribution of the estimators. Okay, sample distributions of the least square estimate. This is okay, we've done one theorem today about R naught squared, but this is something that one can also we'll also do it as for testing and so on and so forth. So this I will do simulations for the one variable case, and then we'll try and see how to say it. So now, first thing you remember, we did maybe a couple of weeks ago. Where we showed this this idea that under normality, the least square estimate was unbiased, and we also computed the variance least square estimate. We showed it's 1/n times the sum of squares by variance of xi and so on and so forth. Right? We did this, and we did for both beta naught and beta 1, and then one could also check, which we did not do last time, is that they are both normal as well. But let's try and see if one could sort of see that. So what I do now is I take 10,000 data points, 10,000 or 100,000. I take x is uniform between 0 and 20, and u is normal. Okay, let's do this. This is my data set, and then my model is y is minus 2 plus 3.5x plus u. That's the model I'm taking. Right. Then I created data frame population. I just put x and y there. Very good. Now, what is happening here is that I've generated true population, this is my true population that I have. And of course, it typically will be random, but right now, this is what I know y and I know x. Let's say that's what I know the error. So let's compute the sigma squared beta naught and beta 1 from, let's say, if I sample from this in a normal way. Let's see. So take n to be the 100, right? Okay. I took hi to be compute the variance of beta naught, hi to be 1 minus this is the variance of beta naught is beta naught is this one, and variance of beta 1 is this one, right? What I get. So what do I get? I get beta 1, and let's see how it looks like. It's 0.04 pointing, and this is 0.02. Very good. So now, okay, this is. Let's assume now I do not know the true values of beta naught and beta 1. Okay, so that is, I'm not able to observe the whole population. I can only observe a random sample of them. Then I can't go and compute the true parameters, but I could obtain estimates for beta naught and beta 1 from the sample using least squares. However, the estimates we know that are outcomes of random variables themselves, and since they are sort of from a sample of a population, so then we know that how the variance will behave and how the distributions will change, given the sample distribution, how it will be. So let's try and do a simulation for this. So what I do is I take a sample size of size 100. I do 10,000 repetitions. Okay, that's what I'm going to do. So I'm going to repeat it 10 times, and I'm going to store all the data in a matrix, a 2-column matrix with rows repeated. And for each repetition, I'm going to sample from the population, right? And I'm going to fit the data set. Okay, and I'm going to capture what the coefficients I get, the intercept and the slope for each of them. That's what I'm going to do. That's what I'm going to do in this simulation. Let's do that. So 100 samples, I repeat 10,000 times. I store data in the fit. Let's just look what fit looks like. Fit will look like, let's say, will look like 2 columns. And then in each column, I'm going to store the first column, I'm going to store the intercept, and second one, I'm going to store the thing. Let's go do this. Let's do for I in 1 to rep. Let's do 10,000 repetitions, and let's do this. This is what we do. Let's see if it finishes. It's not finishing. Let's wait till it finishes. So what are we doing? We're taking the number of repetitions to be 10,000. We initialize a matrix for fit. We run least squares for each repetition, and each repetition we sample 100 points from the known data set. The data set is given by this one. And we already saw the true variance of beta naught is this, the true variance one is this from this data set. Let's look at fit again. Fit will be all these numbers that we have, right? Very good. Very nice. This is what we get. So then let's try and see how the variance of the fit is. Is it in each column? So the first one, so the variance, let's see how it looks like. It's like, it's like 4.18. This will be like, let's do this, and then let's do that one is 0.02. So it's not it's the somehow the intercept seems to have larger variance than the slope. Let's try and do a little bit of a plot. Let's see how it looks like. Let's split the range into two columns, the plot range, and let's do a histogram. Let's see how it looks like. Was it coming? Histogram. So you see the histogram of the beta naught is sort of has a lot of variance as well. It's centered at the correct one and then has this variance. So it's not a and then you do the histogram of the fit 2, it also will have a certain amount of variance. So so in some sense, it sort of supports the bit under our model was what are the model? Our model again was y is equal to -2 plus 3.5 x times u. This is what we modeled on. And we did this least square estimate with sample size of 100, repeated 10,000 times. And we found the histogram looks quite normal, looks centered the correct number, and then sort of has certain variance, which is kind of true to what we found in this expression right here. So our variance estimates support the statements that the close theoretical values. So histogram says that the distribution estimators also can be well approximated by the theoretical normal assumption that we stated before by the simulation exercise. Okay. Now let's do a second study in which we do simulation study 2, this one in study 2. So here what I'm going to do is, that is this convergence, that is as n gets larger and larger, that is the estimators converge to the true parameter that we're interested in. So the unbiasedness is sort of reflected in this. So how do we do this? So what we do is, again, we set a seed. We're going to repeat the experiment 1,000 times. And each time, I'm going to take a vector of sample sizes. So in the first one, I'm going to take 100. Second, I'm going to 250. Third, 1,000. And the fourth, 3,000. Okay. So, and then I'm going to look at the distribution of beta 1 hat. Okay, that's what I'm going to do. And the idea is that for each additional call, you run over this loop of sample size n. And for each of the sample sizes, we carry out the same situations before. You plot density estimate, and for the outcome of each iteration over n, and we check what's going on. Okay, let's try and see. Let's say n is this. Okay, we fit the thing again with so many things. We take two columns again, we split the things in two places. We have the loop running, and for each outer loop and inner loop we run, for each outer loop, length of n, because number of sample size is varying, right? So the whole thing, let it finish. So let's see how it does. So it gives you this thing. So it gives you these 4 plots, right? So what are the 4 plots is? As n gets larger and larger, the variance of beta 1 hat gets smaller and smaller. That's what this is showing. And it's 100, the variance is quite large, and it's 250 a little bit larger, 300,000 a little bit smaller, 3,000 is much, much smaller. So put differently, that see the likelihood of observing estimates close to the true value, this beta 1 is 3.5, right? That's what we had beta 1. Let me go upstairs. This is what beta 1. Beta 1 was in this answer we start off with was 3.5. Right? Beta 1 was 3.5. So if you want to get close to beta 1, you better get at 3,000. That's when you go. Okay. And you can do the same thing for beta naught as well and check. There's no problem. The same solution. I've done this beta naught. You can check the same thing for beta 1. You can plot density 1 and check. Let's just do density 1. Let's change this to density 1 and see if it works. Let's do density 1, and this will be beta naught, beta naught. Let's say. Let's try and do this. Let's go back here. Let's try this from here. Let's try this. What do we get? Beta naught is this one. This one was not coming out correctly somehow. Some mistake I'm making. Let's see. Oh, the x limit is wrong, I guess. This is why. So beta naught was the true value of beta naught. The true value of beta naught is -2. So let's put around -2 and there's x. There is one. Let's go here. Solution 2. X is -2. Let's put -4 to -6. Let's say we'll do this. Then we'll do -4 to -20. Let's say let's do this. Let's try that. Come out correctly. Let's see. Now it comes. Now it's quite good. Right? Last one will be much more. Very nice. So it's close. Very cool. So I've done this both for beta 1 and beta 1. Maybe I'll just do the code. Sorry. -2 and minus. So it's -4 and its variance is quite large. So 2 minus 8. Let's say positive on this side. Let's go to, let's say, at least 3. Let's see what happens. We'll capture the whole thing, I guess. Now it comes correct. Very nice. Very cool. Very cool. So let's just keep this and let's copy this. Oh. This beta naught. Beta was 3.52. It was 3.5. Beta naught was, let's just do 2.5 of it. Beta 1. Beta naught. Beta 1 is 2.5. And the bottom one is beta 1. So it gives you both the graphs. That's quite cool. So as n gets larger and larger, your beta naught hat will converge to true parameter.